Now picture this. Your friendly neighborhood archaeologist just discovered a really ancient bowl and was so excited that he found it, he forgot to take the depth at which it was collected. Now, the sad archaeologist doesn't know how old the bowl is because of that, so he can't be sure if it belonged to an ancient civilization or it was just Uncle Jim squiggling lines on his bowl of Cheetos and burying it. Luckily for you, you read about a technique called carbon dating in the paper the other day, and it said something about magical space rays making unstable carbon isotopes in the atmosphere, which then get eaten by plants just like regular carbon, and have a known half-life of 5,730 years, which is pretty cool, I guess. But then you remember that you have a friend who happens to have an accelerated mass spectrometer, just laying around, so you chip off a piece of the ancient wood bowl and a piece of another one of Uncle Jim's bowls, and after decontaminating the latter from Dorito powder, you send them both to your friends for carbon-14 spectrometry analysis. Spectrometry analysis. Fancy. Much to your dismay, however, your friend decides that since the fourth season of Sherlock is airing today, he isn't going to do any of the calculations for you, and texts you that the bowl contains 1/5 the amount of radioactive isotope as compared to the modern wood. The unappreciative archaeologist, however, upset that you chipped off a tiny piece off of his priceless bowl, is a bit mad, but he says all will be forgiven in the name of science if you can tell him how old the bowl is. So you pull out a scratch pad and a calculator and go to work. Now, you remember from math class that the formula for exponential growth and decay is A equals A sub E raised to the power of k times t. Probably remember it because you always change the starting mass A to R because, that described how well you did on the previous exam. But as you sit there and you're distracted by the TV, you start to wonder, why on earth would we use E to describe the decay of a radioactive isotope? You remember that E is roughly 2.71, but you ask yourself, why that specific number, or why would that be used? You recall that E is defined by some infinite summation with factorials and stuff. But you remember that Bernoulli accidentally rediscovered E when he was trying to calculate the limit of x approaching infinity, of 1 plus 1 over x raised to the x, which as a formula seems very vaguely familiar to you, but you just can't place it yet. So you decide to start seeing what the expression will yield if you start plugging in numbers. Well, you get closer and closer to E, but then you realize what the formula really looks like. It's compound interest, but compounded so much that it's almost compounded constantly. And then you realize that's what E really is. Because radioactive decay happens constantly, it has to be compounded constantly. You scratch your head and decide to write the formula out. A standing for the final amount, A sub 0 being the initial amount, and K being the constant of decay times T of time. But what is the constant of decay? Well, you realize that you need to solve for T eventually to find out how old the bowl is, but for now, since you know that the half-life of the isotope, 5,730 years, and that must mean that's how long it takes for the initial amount to be halved, which means you have all the variables that you need to figure out what the constant is. So you rewrite the formula and use some magical logarithmic properties to cancel out the e and bring down the exponent, and you rewrite the formula solving for the constant. Now that you know what the constant is, all you really have left is to look at what you know. You know that the bowl contains 1/5 of the amount of carbon-14 that the modern wood has, which means 4/5 of it decayed, but you can write the formula as the final amount being 1/5 and the initial amount being 1. Then you simply have to do the same operations as before, except this time solving for t. Take the natural logarithm of both sides, bring the exponents down, ln of e is 1, then you divide everything by the constant, and you get t equals the natural logarithm of 1/5 divided by your constant. And the answer is 13,304.64 years. Now, you really knew that Uncle Jim couldn't really draw that well.